Hello and welcome to Doc Clay's chemistry lessons. We're on a live webinar. It's about 5 to 4 and we're just starting a few minutes early. In fact, we're going to start at 4 o'clock. I'm just setting the webinar off now so you've got a chance to come and log in. So we'll be starting in about 5 minutes time if you want to come along and see what we're doing today. So if you haven't logged in already or gone to the site, do check out our webpage, which you'll find at Dr. Clay's Chemistry or drclays-alevelchemistry.com/quick question, which is where we're presenting from today. Come along and see what's going on. If you go along to the quick question page, you will find the webinar. I'm just going to do some quick sound checks and hopefully you can hear me. Okay, so it's a couple of minutes before 4 o'clock. Hopefully those people who are coming online, if you're in the practical question room, please do just click on the link, say hello, tell me if you can hear me okay, so I can just run through my sound checks. It would be much appreciated if you do. So that would be really helpful if you can tell me that you can hear me okay and that my sound is working. Just while we're waiting, a couple of minutes left. If you're new to the site today, do pop in and say hello. You'll find us here at doclays-alevelchemistry.com. Come to the site. You'll find us in the webinar room here. We're in quick questions for our live webinar today. You'll find access to the webinar live embedded YouTube here. We got our chat below, so do say hello. If you're in the room, it'd be great to hear your questions as we're going through. If you want to join, then please do so. You'll get access to the past webinars, which I'll show you in a second, plus all of our future webinars. The resources for today are in a couple of sections. There's a OneNote resource here. You'll also find the past paper questions, which we've got. You'll find here heaps of past paper questions, as well as importantly the one we're going to look at in key details here, which is from the Specimen paper, the Unseen Specimen paper 3, where we got a question, and a very nice question, on rates of reaction. So that'd be great. Good afternoon, Anon 9350, good to have you on board. Again, for those of you who are new to the site, if you're considering joining, we have twice weekly webinars at 8:30 p.m. on a Monday and a Thursday evening. And here are the topics. Feel free to go and browse those ones that we've looked at so far. And in each section, what you get is you'll get access to, obviously, the webinar. There are then key points links along with past paper questions, and of course important things, a heap of past paper answers, along with the OneNote link with all of the notes embedded within it. So hopefully you find those useful, and it'd be great to have you come along and join us, see what's going on. Like I say though, today we're in the quick question section, and I'll be starting in just a minute. We also have access to all of the resources, which has got all of the YouTube content, video content for the whole of your course, along with key concept questions to help you with your revision ahead of the impending A-level exam coming up in June. I hope the revision is going really well for that. And of course, this site is designed to help you and assist you throughout that process. If you've got any questions throughout the session, I'll put my email there in the chat later on. Feel free to drop me an email if you've got any questions. It's simply chris@drclays-alevelchemistry.com. So we're in, not past webinars, but we're in quick question webinar here, is where all of our links are. I'm just going to move this out the way, and I'll keep an eye then on our chat, and I'm going to start in just a moment's time. So get yourself a drink. If you need to open up the PDF of the relevant questions, feel free to do so, and I'll be about 30 seconds. Okay, hello and welcome to today's webinar on our practical, required practicals. And today we are looking at the rates of reaction, which are required practicals number 3 and number 7. If you're joining the link, just there's a link at the top there. You'll find all of the resources for today's session. I'm just going to minimize my top view here. And just quickly go over here to our required practical section. So we've looked at 1 and 2, titrations and enthalpies. We've looked at 8 and 9, which was EMF and pH calculations. Today, like I say, we're looking at number 3, which is investigating very briefly actually the reaction rate with temperature, and importantly here, number 7, measuring the rate of reaction. So the rate of reaction being one of your A2 topics, or sorry, your year 13 topics, your year 2 topics. We have looked at this a little bit, but we've got some different key questions for us to look at tonight, and we're looking specifically today at the practical element. So I'm going to go over here. We've got a few pages. We're going to start off with the key points. Then we've got heaps of past exam questions. Feel free to sit down and have a go at those in your own leisure. I've created those in the past webinar section, and I'll put the resources, the answers to that at the end on the site. We've also got an unseen paper 3, which we'll work through in just a little bit. Here we go then. We're going to look at the required practicals 3 and 7 and the key points that we've got from hopefully from the practicals that you've done over the course of the year, but also what you need to know for the exam. So this really is from AS level, where we're looking at the required practical number 3, where in AS you really learnt about the idea that the rate of reaction is a measure of the change in reactants or the increase in product over the time taken for them. And there's several ways of measuring that change. We can either do it via a precipitation reaction, where we observe a solid being formed, and the example here where we've got a disappearing cross is the reaction of sodium thiosulfate, or we might have observed here a gas formed, and if we get a gas formed, we'd have measured the volume of a gas that's been produced over a given time. And the other way we can measure a gas formation is if we measure the change in mass in a given time. Now, the problem with the change in mass is that that's going to require very small volumes and a very sensitive balance. So very small volumes or masses of gas, and therefore the best way of measuring a change in gas volume really is using a gas syringe, because you get an observable, viewable measurement, and that's going to help improve the percentage uncertainty in your reaction, because essentially you'll end up increasing your measurement size and therefore decrease your percentage uncertainty. So just to recall, percentage uncertainty is the error in a measurement over the measurement taken times by 100. So when we're looking at gas volumes, gases changing in reaction, we're better off using a gas volume, because that will give us a larger measurement, which in turn will decrease the uncertainty in our measurement percentage. Okay, now in the actual required practical, what they recall us or ask us to do is to measure how the temperature affects the rate of reaction. So how somehow the temperature affects the rate of reaction. So if you're doing this, the key thing that they really want you to get at is that you're going to keep things constant. So ensure variables are constant. So the sort of variables that you might be wanting to remain constant, of course, are concentration there being in square brackets, ensuring you've got volume the same between experiments, and then making sure that you vary the temperature. So if you're asked to describe an experiment, make sure that you've got ways of ensuring constant concentration, constant volume, and vary the temperature. And then also you might want to think about how you measure the end point. So measuring the end point or the end of the reaction. Now that becomes slightly skeptical, because if we're doing a precipitation reaction, so I'm just going to do a big arrow up here. This one, if we're using precipitation where we are assuming that we're going to add some sort of human decision as to when the cross decreases, then we need to think about how we can ensure we're always at the end of a reaction. All right, essentially though, that is everything that we need to know for the practical element of the rate of reaction from the AS. Now that's not to say that you do have to also know the theory side of things. So that's things like your Maxwell-Boltzmann distribution, as well as your collision theory, but we're not going to cover those. We have looked at those in a previous webinar. If you wish to know which one that is, just drop me an email or a private message, or ask me in the chat room. The one that we're going to look at before we look at the actual specimen paper is our measuring the rate of reaction using two different methods. So if we, there we go, zoom in here, just check our required practicals that you've got to be able to, like I say, be able to discuss, recall in the exam. We're looking for two ways. One is by an initial rate method, which we'll see in a second, and the other is by a continuous monitoring method. All right, so the continuous monitoring method really is sort of essentially a bit like our gas volume, whereby we would measure the volume change, or so you measure the change in volume of gas during a reaction, or it could be the mass gas, change in volume of gas with respect to time, and you would then plot a graph of concentration here against time. Now, what we're saying here is we're able to equate our volume of gas, and we're saying that somehow we can make this sure that it's proportional to the concentration of the products. So what that means is we do have to ensure that when we're doing any reaction that we have to keep volumes constant for the whole of our process to ensure that we can say that the volume of gas is proportional to the concentration of the products. What we then get is we can then say, we plot here like we've got is a concentration against time, and here we're seeing essentially we're seeing the products formed. So because we're seeing an increase, we could equally observe this if we were seeing the reactants being used up. So there's no reason why this graph couldn't talk about concentration of, I'll just put in R for reactants with respect to time, and that graph could be going like that. And importantly, we observe the rate of reaction as a gradient. That is the change in concentration. In other words, here, the change in Y, and divided by the change in time. Make sure you're happy with drawing a tangent. That is a straight line that just touches the curve, and from that be able to measure the change in Y divided by the change in X. Now, if you're doing that, that is going to give you a rate at a given time, which is going to be measured as a moles per decimeter to the -3 seconds to the -1. In other words, it's a concentration per time. And what we'll see in an example in just a moment is we can measure the concentration. Measure the rate at different times. So we can look at each point along this graph, or we could take several gradients, measure the rate at different times, and observe how the rate changes with concentration. And from that, I'm just going to make this big so I've got enough room, changes with concentration, and from that we can infer what the order of the reaction is, which we will see in our example question in just a moment. Okay, so that's number one, and that is our continuous rate method. So that is the continuous rate, or the continuous method. The second one, or the second example, is using the initial rate method. And to do the initial rate method, we have to do something called a clock reaction. Now, you may well have done this experiment. This is a classic reaction called the iodine clock, and what you observe is that there is a reaction that occurs, and the reaction is occurring, and then at some point later on, once the reaction has been over, or it's got to a certain constant point, then all of a sudden another product is formed, and in this case the other product is iodine, which immediately turns the substance black in this case. Okay, now to do the initial rate method, we have to follow the following steps. It's called a clock reaction. It's here we go. It's easily estimate the initial rate, time taken for a set amount of product to be formed, and an observable endpoint. In other words, here is our change. And in order to do this, we have to, the concentration of the reactants doesn't change significantly over time. The temperature remains constant, so we need to keep the constant temperature, and when the end point is seen, the reaction has not proceeded too far. In other words, we get the initial concentration. Now, if we're then going to compare different reactions, what we do is we alter the concentration of one reactant and then keep everything else constant. Okay, and then what we do is we repeat this with a different concentration of reactant 1. And what that allows us to do is it gives us two initial rates changing only one thing at a time. Then what we go through and do is we then repeat the experiment again. And this time we are going to change concentration of reactant 2 whilst keeping reactant 1 constant. Okay, and we measure the rate. So in this case, if we were looking at the reaction between hydrogen peroxide, for example, and iodide, we'd be keeping the hydrogen peroxide constant, and we might change the iodide concentration. And then we'd repeat that experiment with a different concentration of iodide, and then we'd repeat again, this time keeping the iodide concentration the same, but changing the hydrogen peroxide concentration. The actual reaction that we look at here is the peroxydisulfate one, where we keep one of them the same, and then we change the iodine concentration. Okay, so those are the key steps for our clock reaction. I'm just going to pause a second, have a quick drink, and we'll have a look at our exam questions. Okay, hopefully you can hear me again. What we're going to do today is we're going to look at this unseen specimen paper 3, because there's a nice example in here of a rate of reaction question. This reaction doesn't use the iodine clock reaction, but you'll find some of those in our past exam paper questions down here. So we'll have a look through these. We'll work through each of the question until we get to the end, identifying the key points. So iodine reacts slowly with propanone in the presence of an acid catalyst according to this equation. So we've got propanone plus iodine forming hydrogen iodide and the iodo product. The rate of this reaction can be followed by preparing mixtures in which only the initial concentration of propanone is varied. So we're only changing this concentration. At suitable time intervals, a small sample of the mixture is removed and titrated with sodium thiosulfate solution. This allows determination of the concentration of iodide remaining at that time. 5 mixtures A, B, C, D, and E are prepared in table 1. So here we've got various different volumes. Note here that the only thing that is changed, well, there's 2 things which are changing: the volume of distilled water and the volume of propanone. But the reason that is these 2 things are changing is because we are varying the concentration of the propanone. All right, so that allows us to alter the concentration. So it then says, then simply doing some basic calculations, calculate the initial concentration of propanone in the mixture A. So here we've got mixture A. What we're looking for is we've got the volume. So you've got to pick out the right data, and you've got to remember that concentration is moles over volume times by 1,000. So you've got to pick out the right volume. 25. You got the times by, sorry, concentration is going to be here. We're looking for the calculate the initial concentration. We got V times C over 1,000, and so we're now going to be calculating here the number of moles. So we got 25 times by 0.1 divided by 1,000, which is giving us the number of moles is 0.025 mole. And then we can work out the new concentration in the mixture, whereby we've got the concentration is equal to the moles divided by the volume times by 1,000. So we've got 0.025 divided by 90 times by 1,000. Now you might have just done this by a dilution method. Either way, you'll end up with a concentration of 0.278 mole per decimeter cubed. Then we got really a practical question: state and explain why different volumes of water are added to mixtures B, C, and D. B, C, D, and E. And the reason that we're saying different volumes of water is to ensure, as we said before, is to make the volumes of the mixtures constant. And what this allows us to do is it means that our volume, as I said in the key points, is proportional to the concentration, and it will allow us to simply plot a volume graph later on rather than having to convert everything to concentration. Now here, don't be slapdash here. You really want to say volume is proportional to concentration. Not just use your shorthand like I have done there. All right, moving on then. Calculate the volume of 0.1 sodium sulfate solution required to react with all of the iodine in 10 cm cube sample of mixture before the iodine reaction. Now, I'm not going to go through this step, but I will give you the answer. If you want to work it through, you should end up with a value of 17.8. I'm not going to go through this step because this should be a reasonably straightforward titration calculation in which we've got a 2-to-1 ratio. If you struggle with that calculation, please do feel free to drop me a line and I'll help you go through it. But I don't want to go through the titration calculations at the moment. All right, now moving on to one of the key things here, which is the sort of skill we need to be able to do come the exam time. Here we're looking at a graph. So we've got some data. We're being asked to do a plot. The result for mixture E is shown in table 2. Volume is the volume of 0.1 sodium thiosulfate solution needed at different times, and T to react with the iodine in a 10 cm cube sample of E. So we've got to plot the data, and it tells us what we've got to do. So we need volume on the y-axis and T on the x-axis. Now, the key thing here, well, we can plot 1, 2, 3, 4. So we can plot time quite happily along the bottom. We got 5, 10, 20, 30. And then the next thing is to decide what to use on the y-axis, and the key here and the marking point is that the scale must ensure that the graph must be at least half covered. In other words, do not start your scale at 0 and go up to 17.5, because you'll end up with a graph that somehow looks a bit like, it's going to look a bit like this, and you're not going to get any measurement from that at all. So your scale should be suitable, and what I'd encourage you to do is probably have something down at about 16. Plot your points up here. I'm not going to go, I'll put some of the points in, make sure these are as accurate as possible. 30 is at 16. Okay, and then depending on what the curve looks like, or whether it's a straight line, tells us here that we want a line of best fit. So this needs to be straight, so use a ruler. Make sure you include your other points. Okay, and then you're going to get a single straight line, because anything which is, if you sort of tend to draw lines of best fit like that, sort of shaving, you won't get a mark for your line of best fit. It's got to be a single straight line using a ruler. And then your next marks are for drawing the gradient and calculating a gradient. It doesn't matter where you do this, simply going the change in y by the change in x. So there I would have said a change in x of 25, and here is my gradient change of about, whatever that is, about 1, whatever it is, change in y. And what you should end up with, the marking points they're looking for, is a gradient, a change in gradient of minus 0.059 to minus 0.061. So there's not a huge scope for error there in your gradient, which means you need to make your graph as large as possible. All right, there you got your 4 marking points. Sorry, 5 marking points. So just to go through those: your scale, your points, your line of best fit, correctly looking at your gradient, and actually calculating your gradient are your 5 marks. Then we're moving on, and here we got our continuous rate method. We got some more data, so it's not requiring you to ensure that you got the gradient correct. It says use information from table 1 and table 3 to deduce the order with respect to propanone and explain your answer. So here we're seeing a change in gradient. Now remember, the gradient is informing us and it's ensuring that we realize that the volume is proportional to the concentration. So the gradient here we can determine, because our volume is proportional to the to the concentration, we can say that the gradient is essentially a measure here of the rate as well. If we go back and actually get some data here, so A, B, so we can then see our volume is directly proportional, so we've got 25, 20, 15, 10, and 6.5. So 25, 20, what was the other one? Let's look up here again. So it's a bit tedious because we've got to go back. 20 and 10. So importantly, B and D here. The gradient between B and D, B to D, as we decrease the concentration of propanone, I should put that in, propanone by 2, we can see here that the rate decreases by 2, and therefore directly proportional, and so it must be first order. Okay, so again, this comes from our theory on rates of reaction, working out the orders. Make sure if you've not seen it, go and have a look at our work that we've done on rates of reaction from the paper 2 organic. Finally, just to finish off, it says each sample taken from the reaction mixture is immediately added in an excess of sodium hydrogen carbonate solution before being titrated with sodium thiosulfate solution. Why would you do this? Well, you're adding the sodium hydrogen carbonate because you've got this is really about looking at what we've got. We've got an acid which is catalyzing the reaction. We know that acids speed up the rate of reaction. So what it is going to do is it stopping the reaction. The sodium hydrogen carbonate, okay, another word here for stopping is quenching. You may have come across before. Quenching the reaction, okay, and by removing the acid catalyst. Okay, so that brings us to the end of the section today. There's heaps of exam questions in the past, exam paper questions on rates of reaction. Do go and have a look. Oh, there's the start of that question again. Sorry. We got more. Here we go. There's heaps more past paper questions here to go through, 14 pages of them, again going through drawing graphs, rates of reaction, so on and so forth. We've also got plotting things like 1/T against volumes. Thanks, Anon, that's great to hear. Just so that you're aware, let me just show you before we log off. Let me just find where you can find all of our mark schemes here. And also what I'd encourage you to do is, if you haven't done so, do have a look here at the question on page 11 here. Question 7 is definitely worth having a look at, because it requires us to use logarithmics. If you have any troubles there, like I say, drop us a line and I'll happily spend a couple of minutes in the session next time. I will upload now the past exam questions. If you've not seen them, you can get hold of all of the exam questions in the quick revision webinar. Just click here, questions here, and from the specimen paper here. Anon 6399, you're great. If you're not signed up already, do come along to my website. It would be great to have you along. The answers to all of these you'll find, as I said, past webinars. Just click on the link. This is, you do need to be a member on this section here to have a look. Rates of reaction, I'm you'll find the answers aren't there just yet, but I'm about to go and update the website now, and they'll be there in the next 5 minutes. That's all from me. I'm live again tomorrow night from 8:30 for our usual webinar where we're looking at Gibbs free energy and thermodynamics. Thanks a lot for joining me again this afternoon. And if you want to share the site with any of your colleagues, please do. drclays-alevelchemistry.com. I'll be around for a couple of minutes before I go. Bye for now.